Ah, est-ce que tu l'as entendu?
Un peu, de loin.
Vas-y, refais parce que j'étais en. C'est moi qui faisais le harcèlement.
D'accord, c'est toi qui faisais le harcèlement, Jérôme.
Ouais.
Je pense que est-ce que ça marche d'ici? Posez les questions.
Oui, ça va. Ouais, j'entends.
Ok, bien.
Si personne d'autre ne parle, j'entends. Ouais.
On a 5 minutes, hein?
On a 3 minutes.
Ouais, il faut que je regarde mes mails. Ça
Ah,
va
bah,
pas être simple, en
vas-y.
fait.
Salut, Karine.
Salut, ça va?
Mhm.
Alors, attends. Tac. Tac. Oui, je pense. Mais
on le met derrière, ça ne dérange pas.
Ouais, je vais essayer de les rappeler alors. Parce que,
je ne sais pas quelle heure ils devaient venir.
10 heures. Non, on a prévu la pause à 10 heures. Alors, attendez, parce que moi, on m'avait dit... Ouais, on m'avait dit ça, hall, salle 102 du premier étage. Ça a encore changé, donc c'est pas ça.
Je vais voir, ça va être... J'arrive.
Ouais, bah sinon, je les appelle. Hein.
Karine,
Oui,
les présentations sont en français ou en anglais?
en anglais,
Ok.
si ça va pour toi.
Ah, pas de problème, non? C'était
Attends.
pour savoir dans quelle langue
Non,
je commençais.
c'est en anglais, on a des anglophones.
Ok.
Tu as reçu notre mail là, à Frédéric et moi, à propos de la table ronde de fin de matinée?
Ouais, ça va être difficile pour
Ça
moi.
va être difficile pour toi? Bon, ok, bah écoute.
Je suis désolé.
Je ne sais pas si Isabelle sera là, on verra. Qu'est-ce qu'il y a?
En fait, je suis en plein, on est en plein consortium meeting LiteBIRD là,
Ah, oui,
en Zoom.
d'accord. Donc
Donc
ça
c'est pas
commence à
facile.
9h, c'est ça, juste après ton talk? Ah bah
non,
c'est
ça commençait à 6h.
Ça a commencé à 6h, bah oui.
Donc je suis bien frais déjà là.
D'accord. Tu es bien réveillé, très bien.
Voilà.
Bon.
D'ailleurs, je suis désolé de ne pas pouvoir y aller hein, parce que, comme tu vois, je suis un petit peu occupé.
Bah oui, je sais.
Ouais, attends, j'ai ça.
Le professeur a toujours.
Moi, j'ai un crayon.
Pour ses étudiants, au cas où.
Je n'ai pas de papier non plus parce que maintenant.
C'est pour leur dire stylo pareil,
Moi, j'ai pris des notes sur mon ordi.
Voilà. Quoi?
stylo pareil. Le prof, c'est énervé. Il a fait une interro surprise, il a créé stylo pareil.
Ah, stylo. Les codes Wi-Fi, tu les envoies à tout le monde?
Je les ai envoyés à PCMI.
Bah oui, mais qu'est-ce que c'est de qu'on en place?
Parce qu'en fait, si les gens prennent tous le même, ça va être compliqué. On les donner à ceux qui ont le premier à Continuum.
Allez, c'est moi.
Tu l'as reçu PCMI hier, donc. Oui, d'accord. C'est une bonne raison. Alors.
Déjà, il va falloir que...
alors, rendez-vous MDT, c'est quoi? Il faut que je sais le tableau.
Je ne sais plus lequel, c'est un des PDF, je ne sais plus.
Un des PDF.
Il y en a 3.
Il y a quelqu'un qui.
C'est moi, c'est moi. Ok.
Ça y est, les gens.
Ok.
On attend quelques 2 minutes.
On attend 2-3 minutes.
Oui, le temps que je suis.
Peut-être pas 10, mais.
Ouais.
Alors, moi, je chair à quelle heure? Parce que du coup, j'ai dit aucune info.
Bah, écoute, c'est Observatoire 1, 2, 3, 4. Alors après.
Non, c'est pas ce PDF là.
Ah, c'est pas ce PDF là. Si, il faut réinventer.
Oui, mais en fait, il y a un tableau dans lequel il faudra mettre notre nom devant le truc.
Moi, c'est
Et après,
ce matin.
Ça ne me dérange pas, donc je vais vous mettre le temps que vous les faites ici la
Non, ça ne me dérange pas. Je vais juste prévenir
le traiteur qui sont censés. De toute façon, on est là, on ouvre la porte.
Oui, parce que lui, il va les reprendre. c'est ça le truc en fait. Je vais changer.
Non, voilà, et après, quand il sera là, je vais passer à la porte.
En fait, je vais le mettre
Ça
sur
vous va? Oui, mais t'as
Comme ça, on manque
Tu vois, pour ça, on est dans le parage, je vais très bien dessiner.
quand ils vont voir que la salle est occupée.
Oui, parce qu'en fait, l'autre côté aussi a concerté, donc ça va faire.
Oui, j'avais compris, il y avait une nouvelle.
Donc, il vaut mieux que ça ait tranquille.
S'il y a une affiche en bas, moi je cherchais un fichier à en bas.
Je fais d'un quart de tour.
Oui, parce que personne ne savait pas.
Observatoire 1, c'est toi, d'accord.
Je vais demander.
Nous, on ne savait pas.
Voilà.
Voilà. Mais non, mais je me demande s'il fallait au moins juste en bas d'escalier mettre une affiche.
C'est arrivé, EB4, observatoire avec 2 S.
Non,
Il y a trop de gens pour les affiches.
c'est vrai que j'ai vu quelqu'un qui met des petites
Moi,
affiches.
il fallait 4 minutes pour me trouver.
Ah oui.
Moi, je fais moi, là.
Je vais mettre carré le photo. Comme ça, celui qui est là, il peut.
Ah oui.
Ah, t'as pas lancé le Google Doc? Le Google Doc avec les questions.
Attends, copie.
Je
Mais ça,
ne
c'est
veux pas casser ton
peut-être que
ordre.
ce soit Jérôme qui gère
Non,
ça.
il a besoin de voir.
Bah, j'ai besoin de savoir pour les questions.
Ah oui.
Bah oui, mais non, mais tu verras pas parce que tu auras ça.
Ah, bah alors à ce moment-là, je vais
En fait, tu n'as peut-être pas besoin d'être là.
Je vais utiliser 2 ordi, voilà.
Parce que quand le configurateur est sans,
Non.
Okay. So, welcome everyone, both live and online, for this last day of our meeting. So we'll start with Ludovic Montier, who will tell us about the future of CMB space missions, i.e. LiteBIRD. The floor is yours.
Okay, good morning. So I wanted to first thank the organizer of the meeting to give me the opportunity to promote the galactic science with LiteBIRD, which is not a galactic mission in se, but I would like to show you how interesting it could be to do galactic science with LiteBIRD and where we are. Okay, get it. So yeah, to start with, I need to remind you all what LiteBIRD is made for. Actually, the goal of the LiteBIRD mission is to look for the inflation period, which is the very beginning of the story of the universe. And so how we proceed, what we are looking at is the imprints of the gravitational waves that would have been produced during the inflation. So at the very, I don't know if you see my mouse. So at the very beginning of the story of our universe after the Big Bang, the assumption is that quantum fluctuations would have produced some gravitational waves that propagates through the universe up to the recombination period of about 400,000 years after the Big Bang, and they'll leave some imprints in the what we call the CMB that we can then recover today. And so this is the full sky map of the cosmic microwave background measured by Planck. And this is the intensity, and okay, got it. And you can also measure the polarization of this cosmic microwave background. And actually, if you look carefully, I think there is a small video here. Looking carefully at the features of the sky, you can see this particular polarization features that you can divide into two modes, what we call the E modes and the B modes. And most of the sky is made of E modes, actually. And the reason why is simply that the E modes are associated with the density fluctuations of the early universe, and with matter falling into the gravitational wheels and producing these kind of E modes. On the contrary, if you have some gravitational waves at the period of the recombination, you will produce both E modes and B modes by propagation of those gravitational waves in the medium. So the path is the following. If you have an inflation process, which is still an assumption, you may have quantum fluctuations of space-time producing those primordial gravitational waves that will lead to those kind of vortex seen in the CMB polarization that we call the B mode. And looking for B modes, you can then trace the information back to the inflation history. So this is how LiteBIRD has been designed. But when you look for gravitational wave signal, so when you look for B modes, you have to be very careful. And you may remember this famous history now with the BICEP2 Keck experiment in the South Pole, where they detected very nice B modes actually at 150 gigahertz. It was in 2014. And so it was the best detection event ever of B modes actually. So it was really a success. The only issue is that you have to be very careful with the galactic foregrounds. And in this picture, you have at the center the detection of the B modes made by the BICEP2 team. And as a background, you have the Planck map at 353 gigahertz, which traces the dust emission and the galactic emission due to polarized galactic emission due to dust. So the issue is that actually this emission is not a background, but it's a foreground. So when you look at for primordial signal, you first have to go through this galactic emission. And actually, when you look at the Planck map at the same location at the BICEP field, you can find also very strong B modes coming just from the dust emission. And just switching between the B modes measured by BICEP2 and the ones measured by Planck, you can see already by eye a very nice correlation between both. And actually, what BICEP2 has measured was mainly dust emission. And this is why they managed finally to put the upper limit on the primordial B modes detection, which is given below. So this is just to illustrate the fact that when you are looking for this primordial B mode signal, you have to deal with the Milky Way emission, and this is really a nice feature for the galactic experts, because they cannot I would say cosmology cannot go without a very good knowledge of the galactic foregrounds if they want to have a reliable detection of the primordial B modes. So in this context, the LiteBIRD mission has been designed, and actually the LiteBIRD mission is a strategic L-class mission at JAXA that has been selected in 2019. And so it's it's a second L-class mission, the first one being the MMX experiment that will go to explore the Martian moons exploration in 2025. So as you can see, this second L-class mission LiteBIRD has been selected in May and should be launched by the end of the decade, typically. So this mission will be launched in L2 orbit, so Lagrange to orbit, with an all-sky survey of 3 years. So again, it's really a all-sky survey as the other CMB missions, actually. And there is a large frequency coverage. I will come back on that, because this is really where the benefit comes from the galactic science. So spanning from 34 to 448 gigahertz. And with 3 instruments, I will come back on that, with the following resolution. So at the high frequency, you get something around 20 arc minutes with a bit more than a degree for the lowest frequency. It has a very strong sensitivity in polarization, and this is the key point. It's about 100 times better than what we did with Planck, actually. And to achieve that, we really have a design focused on polarization. I will explain a bit more. So few words on the payload, because it's important to understand what this mission is, how this is designed to and how this could be used actually for making interesting science after that. So we have 3 telescopes, as I said. So the low frequency telescope in the bottom, which is under JAXA responsibility, and the mid and high frequency telescopes on the top, which are under European responsibility. And even more than that, it's under CNES leadership so far. So all the telescopes are cooled down at 5K, just to minimize the impact of the semantics. So they are extremely sensitive, and they are properly designed for polarization measurements, and this is the key point. And in order to optimize this kind of measurements, there is a continuously rotating half-wave plate, which is the first optical item component of the optical chain. And so this is thanks to this component that we can get rid of the 1/f noise, and we can have very reliable polarization measurements on the detectors. So you can see on the right the prototype of such a detector, which has been designed in Tokyo for the LFT. And the challenge for this kind of hardware is that it has to be magnetic sustentation in space without too much heat load for the instrument. So this is one point about the polarization measurement. The other one is that we deal with focal plane with detectors already sensitive to polarization. So the idea is to have multi-queric detectors that are already polarized sensitive. And you see that we have more than 4,000 TS detectors distributed over the whole frequency range into the 3 telescopes. And in order to optimize the space of the occupation of the focal planes, the detectors are designed as multi-queric. So each detector can get 2 up to 3 frequency bands with polarization. So actually each detector mimics 6 sensors in the end. So this is a quite powerful implementation of the focal plane. And even more than that, so the mission is designed for the polarization measurements of the foreground. As I stated before, this is really the key point. So it spans from very low frequencies, 34 gigahertz, up to 448 gigahertz. And the high frequency telescope is really focused on the highest frequencies, spanning from less than 200 up to 448 gigahertz. And this is only possible from space, as you know, because of atmospheric absorption from the ground. So this is really what the space mission can offer. It's going up to those high frequency to cover the dust emission on the side, and to the lowest frequencies to cover the synchrotron emission on the other side. And this is what we can use for the galactic science, as I will describe just after. A few words about the collaboration from which we are a key partner. So I will not enter into the detail here, but you can see that it's an international collaboration with leadership from Japan. Of course, it's a JAXA mission, but there are key partners in US providing the focal planes. They're also in Canada. They provide warm round-without electronics. And of course in Europe, because we are delivering the mid-frequency and high-frequency telescopes, where the France is responsible of the last step of the cooling chain with the sub-Kelvin cooler, since the focal plane are cooled down at 100 milli-K, and responsible of the whole delivery of the mid and high-frequency telescopes. So this is clearly an international collaboration. We are about 300 researchers so far, with a strong involvement of European people. More than half of the collaboration is now European. And France is deeply involved in this, and you can see in the bottom of the chart here that the French team is deeply involved in this collaboration. So just to say last word on that, we are 12 now laboratories involved in LiteBIRD in France, with about a bit more than 50 people involved in the both hardware and data analysis parts of the mission. And this is quite broad coverage of the lab interested in CMB science. And important point, we entered into CNES phase A1. It was in 2019, and we are now in what we call the phase A2 up to end of next year, before decision to go into phase B. So, and CNES has taken the leading role on the MFT and HFT instruments at the European level. Okay, so now more first on the scientific outcomes. So I will go very quickly on those first, which are cosmological objectives, just to stress that the goal is to reach a sensitivity on the tensor to scalar ratio R, which is measuring the presence of gravitational waves, to an uncertainty of 10 to minus 3, just to say that the better parameters we have today are a few of 10 to the minus 2. So it's more than a factor of 10 better than what we can do today from the ground. And I have to say that it's really challenging even to reach this 10 to the minus 3. And this is mainly looking at the highest scale on the sky. So it's not a high resolution mission, but it's really looking for the large scale of the sky. And when you design this kind of focused mission, because the goal is really to get to have a detection of the gravitational waves imprints in the CMB, you have very stringent requirements on the design, and finally you can offer a very broad science case just because you are focusing on a very stringent objective, which is the detection of R. So in the top of this, you see 15 all sky maps that we will use to produce this CMB polarized map that will allow us to get this sensitivity on R. But using those 15 maps, you can do many things. Of course, you can do cosmology on the side, on the left of the panel. You can do extragalactic science on the right, like CIB, cross correlation with other missions, or even Stoyanov-Zeldovich spatial distortions. And you can do galactic science. And I will detail what we could do for the galactic science. And this is typically the heritage of what happens for Planck, where we had less bands, but it was the first time, and we had such whole sky maps in polarization also, and this really opened the door to new discoveries in galactic science. So this is a quick view of what was done with Planck. Actually, you see the two main outcomes of the component separation of Planck, with the synchrotron map on the left and the dust polarized map on the right, which comes from Planck. And this is from this kind of map that we learned a lot. And on the main objectives, we can list here the characterization of the foregrounds SED, and you can consider them as foreground when you're a cosmologist, but you can really consider them as interesting per se components. And we get inputs on the large scale galactic magnetic field. You can make progress on the models of the dust polarization grains, and you can look at the early stages of star formation. So this is just a quick comparison of the LiteBIRD performances compared to Planck. So here you have the sensitivity in polarization as a function of the various frequency bands. And the size of the symbol gives you the full research maximum of the corresponding instruments. So in yellow, you have the Planck ones, and in light blue, you have the LiteBIRD ones. So you can see that you have a gain in sensitivity about a decade, about the whole range. You have a better frequency coverage with 15 bands instead of 7. And you have a gain of about a factor of 30 in signal to noise ratio in the highest frequency bands. And then you see that there is still a difference between the resolution you can get with Planck. You can access better resolution with a lower full grid search maximum. So what you can do is to smooth the Planck maps at the same LiteBIRD sensitivity, and this gives you the orange discs here, which just tell you how we have to degrade the resolution to get the same sensitivity. And so you see there is a clear benefit with LiteBIRD to reach a given sensitivity with much better resolution. Actually, that's what we could do with Planck. And another way to go is that with Planck, as you may know, we have finally used a degraded resolution for most of the galactic analysis. We've smoothed the Planck maps up to 80 arc-minutes. And if we do the same with LiteBIRD, and this is now the dark, blue discs here, you still have an improvement in gain compared in sensitivity, sorry, compared to the Planck case, but you have a much better homogeneity over the whole frequency range, which is extremely important when you want to have to put large constraints over a large frequency range on the SCD. So another way to look at that is this this plot, which is part of the review collaboration paper that should be submitted very soon. So in the PTEP journal. So in this plot, you can see as a function of the column density on the y-axis and of the resolution on the x-axis, you can see the number of bands you can access with a minimal signal to noise of 1. So I don't see, no, you don't see my mouse anymore, but you have in red the contours of the Planck mission, for which you are clearly you have a limited domain and a limited number of bands you can access with a sufficient signal to noise ratio. On the contrary, you have the colored contours. With LiteBIRD, you can access many bands, even in the diffuse medium, and this is what we try to explore here. So on the very lowest part, you can explore the diffuse medium at intermediate, at quite good resolution. Then on the top, you will access broad multi-frequency analysis in bright regions at a degree scale, roughly. And on the top right, you can still access in the quite diffuse medium at large scale, broad multi-frequency analysis. So we clearly gain a lot in the spectral range with LiteBIRD compared to Planck, but we also gain in the sensitivity in the diffuse medium. So how can we use such performances? We should be able to put some interesting constraints on the dust grain properties, for example, and answer some key questions that are still open about the ferromagnetic inclusions, for example, or a single versus multi-component models of dust grains, which is another open question. And a comparison with laboratory measurements may be even more accurate than what we could do so far with Planck data, for example. And then on the synchrotron emission side, we may put some more stringent constraint on the spectral index and its variation over the sky. Another interesting aspect is the anomalous microwave emission, and so far we don't have any detection polarization of the AME or statistical ones. We don't have clear detection yet, and this would clearly help to put new constraints on the nature of this kind of emission. And for this combination with radio experiments like CBAS, Quixote, or ESPAS, datasets would help a lot to put constraints on this IME. A last interesting question we would like to address is the spatial variations and the line of sight effects. And actually, we could explore with this kind of whole sky survey the spatial variations of grain composition. But to do that, we have to be very careful because, as you know, there is a strong coupling of the dust polarized emission with the 3D structure of the magnetic field. So we have to be very careful on that. And actually, we clearly have to tackle both aspects together. And this goes to the next interesting aspect, is that we can investigate the interplay with the magnetic field. And so this is here a comparison of the drapery features we've been producing with Planck on the left, and what we could do with LiteBIRD on the right as a almost equivalent frequency. So first, you can see that in the brightest regions on the bottom of this figure, it's in Polaris actually, we cannot gain much with LiteBIRD in these bright regions where the signal to noise ratio in Planck is high enough to get the relevant information. So we won't gain much in those regions with LiteBIRD. On the contrary, for the diffuse region and the outskirts of these molecular clouds, you can get a much better signal to noise ratio, and you can explore these mid-scale diffuse regions around this star-forming ones. So this is where the LiteBIRD would help with full mapping at the original resolution of LiteBIRD of the polarized structures and the connection with the magnetic field. So yeah, as Planck did, LiteBIRD will go even a step further and provide unique polarization maps of the whole sky. That will become the new gold standard for analysis of magnetic fields in the diffuse ISM. So just to remind you that for the dust emission, we have an improvement of Bode factor of 10 at high frequency compared to Planck. So it will really help to understand the interplay between turbulent gas motion and magnetic field. And the comparison with MHD simulations, for example, which is not satisfactory yet. Another interesting aspect is the study of parity violation from the dust alignment on the magnetic field. And some recent analysis have shown that there are some parity violation, but we don't know if it's just random fluctuations or it's really associated to a generic turbulence feature. So using LiteBIRD data, we could really put some more reliable constraints on the origin of this. And this may have an impact for the cosmic barrier inflation forecasts for cosmology, actually. Concerning synchrotron emission, the LiteBIRD sensitivity is improved by a factor of 5 at 40 gigahertz compared to Planck again. So it will help to build some robust correlation between dust and synchrotron polarization. And this goes to the last point, but not least, which is the 3D modeling. And having in hand both dust and synchrotron maps will help to build the correlations toward the modeling of the 3D structure of the galactic magnetic field, in particular at high latitudes and in the solar neighborhood. So more concretely, what's happening today inside the LiteBIRD consortium? We've been created recently what we call the LiteBIRD Galactic Science Project Study. So this has been created last June, so it's really recent.
You are running out of time.
Oh, I'm sorry, I'm done. It's my almost last slide.
Almost last slide?
Yeah, I have the conclusion after this one.
Okay.
Just to say that this is the important point of today, because the goal of this group is to gather LiteBIRD people that are interested in galactic science and to assess the feasibility of galactic science using LiteBIRD data. So we have objectives to model, and you have the list here of what we would like to model. 3D structure of the magnetic field, but also physical conditions, the line of sight, dust grain properties, and so on. And for this, we clearly need some expertise from galactic experts. And we have some in the collaboration, but of course not enough. So this is my take-home message and my last point. And I will directly go to the bottom message of this this slide, which is that the LiteBIRD collaboration is widely open to experts in galactic science. And thanks to the creation of this galactic science project study, the door is open to the galactic science inside LiteBIRD, and people are really welcome to participate and as LiteBIRD members of the collaboration. So this is really a message I wanted to convey today and make you know. And I'm done. Sorry for being late.
Thank you, Ludo. We'll take a few questions. Martina has a question. So.
Yes, I was wondering who provides the TS detectors.
Transistor edge sensors. So this is.
Would you know?
Have you heard my answer? Yeah.
No, sorry.
Transistor edge sensors. So this is a technology that is used.
Ludo, the question is who is providing them?
Oh, sorry, I didn't get that. It's the US again. So the US is responsible of the focal plane delivery.
So it's NASA Goddard?
Well, it's not yet NASA Goddard because NASA is not yet committed to the project, but NASA has supported technical development in the lab in Berkeley, so LBNL, and the team of Adrian Lee and people in Colorado, the NIST, are developing the focal planes today using this support from NASA. But there is not yet NASA commitment. Actually, well, as you may know, people are waiting for the Astro 2020 decadal, which will give the next priorities of the US developments. And NASA is waiting for that before committing to LiteBIRD officially for phase B and further.
Okay, thank you. Thank you very much.
There's a question by Jérôme.
Yes, it's been unclear to me what are the natural angular resolution of the telescopes at the different frequencies.
Here we are. So for the highest frequency range, so from let's say 160 to 450 gigahertz, we span between 30 arc minutes to 20 arc minutes, roughly. And at the lowest frequency range, you are more above the, you go up to the degree scale.
Thank you. Thank you, Ludo.
Welcome. Thanks to you.
And have a good screen-to-screen meeting.